Okay, so this is the outline of chapter 31, so about the LC oscillations. Okay, so the whole chapter is about the RLC circuit. Yeah, and the first part is about the LC oscillation. So yeah, it is an analogy to the simple harmonic motion for the mechanic system. Yeah, actually, and then we also learned the damped oscillation in the RLC circuit. So with the R in it, so there will be some energy loss in between. So the oscillation will become will decay gradually, and then the forced oscillation of three simple circuits. So actually, this part we will learn the phasor. Okay, we'll learn the phasor. So actually, using a complex number to represent a sinusoidal function. Okay, so actually complex number have a real part, imaginary part, but it can be also represented as a polar form, which is the modulus with the angle. Okay, so actually for sinusoidal, you can also have an amplitude and also a phase. Okay, so correspond to a complex number. So actually, we can by making use of the phasor, we can simplify the calculation. Okay, if it is a time domain function like sine of something, cosine of something, so definitely we need to use we need to solve the constant coefficient in the ODE. But if we introduce the complex number known as the phasor here, so we can just solve this kind of circuit by some algebraic calculation, but we need to go to the complex domain and then finally convert this complex number back to a sinusoidal. And then finally, the power in the AC circuit, and then transformers. Okay, so here, okay, so this is a big graph. Okay, so we have 8 subfigures. Okay, 8 subfigures. So it represents electromagnetic oscillations. So here we have 8 stages in a single cycle of oscillation. Okay, of a resistance. Okay, without resistance, LC circuit. Okay, so here you just start from here. We have an L, we have a C in series. Okay, an inductor and a capacitor in series. So at the very beginning, we should have some initial condition. So we consider the initial condition to be all the energy are stored in the E field. Okay, so actually, if you still remember, okay, so capacitor store the energy in the E field, and then the inductor is store the energy in the B field. Okay, so actually at the very beginning, all the energy are stored in the capacitor. So which means that so you can also consider this P is this energy is half of CV square, and then actually this one is half of Li square, half of Li square. So which means that if we don't have any UB, okay, so I is zero, and then there will be V across the capacitor, which means that we have some charge, okay, pre-charge on the capacitor. So this is the initial state. So in this state, the charge will tend to going out, okay, tends to going out. So there will be current going this way, going in a counterclockwise direction. Okay, so in that case, this V becomes smaller, okay, because there are less charges on the capacitor. So it will be like, okay, after some time, so actually the UE is decreasing and the UB will increase because there are some current going through. Okay, so the current becomes larger and larger, and then the charge becomes smaller. So UE becomes smaller and smaller, and then UB becomes larger and larger. So at a certain moment, okay, this moment is not necessarily that important. So, but anyway, it just tells you that, okay, so maybe for a moment, UE equals UB. Okay, so it's like yeah, so half of the energy transferred to the inductor. Okay, transferred to the inductor. And then, okay, even sometime later, okay, all the energy transferred to the inductor. Okay, so at a very specific moment, okay, there is no charge, okay, on the capacitor. So UE is 0. So and then at the moment, UB is maximized because all the UE transfer into UB. Okay, and then it will have a maximum I. Okay, so yeah, so just as what it mentioned is that it's a resistance circuit. Okay, so there won't be any energy loss. So it will be like the energy here is oscillating between the E field and B field. So yes, so something like that, and then later on, this current becomes smaller. Okay, start to decrease, but in that sense, there will be some positive charge on the bottom plate. Here, the positive charge is on the top plate. Okay, so it's something like this. Even though so it's like half of C negative V squared, but negative V squared is the same as V squared. So for the energy point of view, you can see positive or negative. But actually, for this stage, okay, so actually positive charge are stored on the bottom plate. And actually, there will be a moment that the UB equals UE, so on and so forth, and then until this moment, I decrease to 0, and then all the energy turns back to the transfer back to the capacitor. But this one and this one, okay, so the charge are on the opposite side, but it will take a similar step and then go back, okay, and then back and forth. It will oscillate forever, as much as there are no energy loss. Okay, so here it says UE will be Q squared over 2C, or half of C squared, depending on what variable you want to use. And then UB will be half of Li squared. Okay, so this is what we have learned in chapter 25 and chapter 30. Okay. So here is an analogy, okay, to the textbook call it a block spring system. Okay, I tend to call it a spring mass system. Okay, although they are referring to the same thing. Okay, so so actually for this block spring system, okay, and then also the LC oscillator, okay, there are some similar things, at least high inside the mathematics. Okay, so actually for the spring, okay, it has a potential energy like half of kx squared. Okay, half of kx squared. Okay, so and then the block, okay, will have a kinetic energy half of mv squared. Okay, so this is the adding them together will be the total mechanical energy. Okay, total mechanical energy. We also assume that there won't be any frictional force, there won't be any energy loss in between. So in that case, we have these two. Okay, one is potential energy, one is kinetic energy. So add up to be the mechanical energy, and then we assume it will be conserved. And then here we also have a v equals dx dt. Okay, so the displacement, taking the derivative of the displacement, will be the velocity. Okay, for the LC oscillator, we have a capacitor storing the half of q squared and then 1 over c here, and then okay, so this one just to mimic this form. Okay, so like a half of something Okay, so this something is k, this something is 1 over c, and then variable square, okay, x square, q square here. And then for the inductor, it has half of Li square, and then also we have this, the derivative of the charge will be the current. Okay, so here is just tells you that Q correspond to X, 1 over Z correspond to K, I correspond to V, and L correspond to M. So it actually means that if you have learned some formula for the broad spring system or springless system, you just need to change the variable, okay, according to this, matching table. Then you get the version for the LC oscillator, okay. So and in that case, we have omega equals 1 over square root of LC. Okay, so this is a well-known oscillating frequency for the LC oscillator. Okay, so actually, the textbook just lets you know, okay, how to really derive it. Okay, how to derive it. Okay. So actually, in the last chapter, I mean, for the chapter 27, it also mentioned the energy method. At that time, the energy method looks so stupid. Okay, I think. Okay, so here the energy method is, I think it's quite interesting. So here, let's take a look. Okay, so the U is the total energy, and then it consists of UB and UE, so which is half of Li square and then Q square over 2C. So this is the total energy in the LC oscillator system, and then there won't be any energy loss. Okay, we assume there are no resistance in between. Of course, in the real world, it is not possible. But yeah, this case is just for simplicity. Okay, so so here it just mentioned that the circuit resistance is 0. So no energy is transferred to thermal energy, okay, which means no energy loss. So U remains constant with time, okay, so which means that our du dt is equal to 0, conservation of energy. Okay, so actually we can just, okay, so we have U here, so we can take the derivative on both sides. So du dt is actually like taking the derivative here. So L is a constant, C is also a constant to time, and then this is I squared, so it becomes 2I, okay, 2I, 2 and 2 cancel, so Li, and then we have the chain rule di dt. Similarly, okay, C is a constant, and then taking the derivative of Q squared will be 2Q, okay, so 2 and 2 also cancel. And then, so Q goes to here, and then the chain rule, okay, dQ dt, okay, something like this. So it turns out to be like, yeah, actually this dQ dt is actually I, okay, so, yeah, so I and I just cancel. And then this di dt, we can just turn it into d2q dt2, okay, the second derivative of the charge with respect to time. Yeah. Okay, so you just make use of this, okay, I equals dq dt, so taking the derivative on both sides, di dt is d2q dt2, okay, plug it into here, okay, so we replace this one, and also this one, okay, so we can cancel something. We just assume that I won't be 0 at all the time, so we can cancel the I. Okay, and then later on, after finish the cancellation, we conclude that, okay, we have this second order constant coefficient linear ODE, okay, as the second derivative of Q plus 1 over LC Q, okay, equals 0, equals 0. Okay, so actually we can also use the potential method to derive the similar thing. Okay, although I'm not using the variable of Q, okay, but actually this is a linear system, so that it is free to change to different variable. Okay, later on you'll see what I mean. Okay, so here we have a L, we have a C. Okay, maybe I put it here. Okay, and then we have a V. Okay, let's make it like this. Okay, okay, so no, this should be okay. Okay, you feel like this is a little bit strange. Okay, so what I mean is that, okay, so this is 0 volt. Okay, so this is 0 volt. So this is V. Okay, so if we consider this side, okay, this plus side minus this side, okay, so will be V minus 0 will be V. Okay, if we consider this side is 0, minus V will be negative V. Okay, you may consider it's a little bit strange, but you'll see why. Okay, so actually, for the capacitor, we have I equals CdV dt. Okay, I equals CdV dt. And for the inductor, actually the current is like this. Okay, so pay attention is that for the current and the voltage direction, it needs to be from the positive to negative. So in that case, this negative V equals L di dt. Okay, so just write it explicitly so that you won't, you will be easier to avoid these mistakes. Okay, so so actually we can just put this thing to here. Okay, so we have a L d dt, and then we have C dV dt. So C is a constant, so we just put it outside. So we have a LC d2V dt2. Okay, it's like this. So so we can actually slightly rearrange. So we can just take a look at this side and also this side. We move the negative V to the other side, and then divide LC on both sides. So we have a d2V dt2 plus 1 over LC V equals 0. So actually this one and this one look alike, okay, but not the same. So just as what I mentioned is that, okay, so here is Q, here what I put is V. Okay, so in a linear system, okay, so any variable, as long as they are linear, so they will also satisfy the same homogeneous equation. They will satisfy the same homogeneous equation. So yeah, so you can actually use the linearity, or just as what I mentioned for the supplementary nodes, okay, to actually prove it, okay, or actually verify it. So I don't try to spend too much time here too. But the idea here is just you can just replace this V as I or replace it as Q. Okay, so they're actually the same. Okay, so if we or in other words, if we have an equation like this, we can also write it as d2I dt2. Okay, plus L over C, I equals 0. Something like this. Yeah, because the idea will be like, okay, if we try to prove this to this one, it will be easy because it will be like, actually you can just take derivative, okay? Just take one more derivative and then multiply by C, okay? So you will construct some C dV dt here, okay? C dV dt here, just turn out to be an I. And then C, okay, and then d3V dt3 here, okay? Turns out to be the second derivative of I, okay? So yeah, you can always try to transform the homogeneous equation from one variable to another variable inside a system. Okay, so So when we consider a spring mass system, I'm not sure that whether you have learned the derivation before. Okay, so just let me do it quickly. So here, let's just assume we have a spring and connect to a mass m. Okay, so we have a force acting on the mass. So this force will be negative kx, okay, according to the Hooke's law, okay, Hooke's law. And then according to Newton's second law of motion, we have F equals m d2x dt2, okay. So F equals ma is something like high school student use it, okay. So for bachelor student, you should be able to use the derivative form, okay. So F equals m d2x dt2. Okay. So in that case, we have m d2x dt2 plus kx equals 0, and then we divide m, okay, for the whole formula. So we have d2x dt2 plus k over mx equals 0. Okay, so for this one, s squared, okay, second derivative turns out to be s squared, and then, okay, k over m, and then the original function, change it to 1, okay, so it turns out to be like this. So s will be like plus or minus j square root of k over m, okay, so this is complex conjugate roots and pure imaginary roots here. Okay, so actually this omega will be k over m, okay, for the spring mass system, as you have learned it even in high school physics. So here similarly, we can make it like s squared plus 1 over lc equals 0. So s will be j square root of lc. So here we have omega equals 1 over square root of lc. You may ask why it's like that. Okay, if you still remember when we talk about how to solve the homogeneous equation, if it is a complex conjugate root, so it turns out to be like, for example, here will be like v will be like a cosine of omega t plus b sine omega t, okay, where omega equals 1 over lc, okay, something like this. Okay, even for here, if we make the omega to be like this, you can also have this x to be a cosine of omega t plus b sine of omega t. They are similar. And actually, in high school trigonometry, you can always make it like r cosine of omega t plus phi or minus phi, depends on what you like. Okay, so for the combination of cosine and sine with the same frequency, we can make it a single sinusoidal with a different amplitude and a different phases, okay, and a different phase. So yeah, you can always make it like that. Okay. So that's why for the textbook, it just derives this one, and then it tells you that, okay, the solution will be like this. Okay, so actually we actually need to solve the constant coefficient ODE, okay, like this, and then we can actually change it to something like a v cosine of omega t plus phi, something like this. So here it's just like taking the same form. Small q will be like the amplitude of the charge, okay, capital Q cosine of omega t plus a phi, okay, with a phase. So here, if you would like to calculate the I, will be like taking the derivative of the Q taking the derivative of the q, so it turns out to be q and then cosine of something, okay, the derivative of cosine will be negative sine, okay, so negative sine omega t plus phi. But we have the chain rule, okay, we need to multiply by the omega, so we have an omega in the front due to the chain rule. So I will be negative omega q sine of omega t plus phi. Okay, so which means that q and I will have some relationship. We have some relationship. Okay, so here it just tells you that UE will be q squared over 2c, okay, and then you plug in these expressions, 3112 to here, okay, we will have a q squared over 2c, and then cosine square of omega t plus phi, okay, so this is the energy stored in the E field, and then for the magnetic energy will be half of Li square. Half of Li square. Half of Li square will be like half of UB will be half of Li square will be half of L, and then I square, okay, we have a negative side square will be positive, so I just ignore it. So it turns out to be something like this. Something like this. Okay, so don't forget that omega is 1 over LC, so which means omega square is 1 over LC. Okay, 1 over LC. So which means if you just put L to the other side, so L omega square will be 1 over C, so which is this part. Okay, which is this part. So C goes to the denominator. So it turns out to be q square over 2c sine square of omega t plus phi, which is actually the same as this one. And then, okay, so there comes out some interesting thing is that, okay, so in high school trigonometry, almost the very first formula you will learn is, or the very first identity you learn is sine of something square plus cosine of something square turns out to be 1, so which means that UB plus UE will be q squared over 2c. So so here it just so at the bottom it just tells you that UEUT for this case of phi to be 0, yeah, because phi is just a reference. Okay, so you can just take a suitable coordinate system, so that okay, you can always eliminate phi, okay, if there's only one signal with phase. Okay, so in that case it will be okay, so it will be okay to take phi to be 0 to make things easier. So the first observation will be the maximum value of UEUB are both q squared over 2c, yeah, because the maximum I mean the range of the sine and cosine are between -1 and 1. Okay, so taking the square, okay, which makes the maximum value of sine square of cosine square to be a maximum of 1. Okay, so in that case, both have a maximum value of q squared over 2c. So at any instance of the sum of UEUB equal to q squared over 2c, yeah, because sine square plus cosine square is equal to 1, so a constant. But when UE is maximum, UB is 0, and conversely. Okay, so this is actually this figure. So one is cosine, one is sine square, one is cosine square, one is sine square. So if you are familiar with a trigonometry, so cosine square x will be like half of 1 plus cosine of 2x, and then sine square will be like 1 minus cosine 2x over 2, something like that. So you can see, okay, here is actually the 1/2, okay, and then plus or minus the cosine of 2x. Okay, so here we have a sample problem. So here it says a 1.5 microfarad capacitor is charged to 57 volt. So the charging battery is then disconnected, okay, and then a 12 millihenry coil is connect in series, okay, connect in series with the capacitor, so that LC oscillation occurs. So it just try to tell you how it saw some energy in the LC system. So it just connect the capacitor to a battery, so that there will be some charge pre-stored in the capacitor. There is some energy stored in the E field, and then disconnect the battery and then connect it to the inductor, so that there will be energy pre-stored in the LC oscillator. So what is the potential difference? VL of T across the inductor as a function of time. So as long as we have a D2Q dt2 plus 1 over LCQ equals 0, we also have this Q equals capital Q cosine of omega t. Of course, it should have a plus phi in general, but we can actually but for many cases this phi is not important, so we just take phi to be 0 here. Okay, and then Q will be equal to CV, so which will be 1.5 times 10 to negative 6, and then times 57. So it turns out to be 8.55 times 10 to negative 5 coulomb. So this is the charge at the very beginning, okay? So VL will be L di dt. So L d dt, and then I is actually the derivative of Q with respect to time. So we have actually L d2Q dt2. Okay, so actually what it means is that we have the expression of Q here. So we need to take the derivative with respect to time for 2 times, okay? So it turns out to be cosine turns to be negative sine, and then turns to negative cosine. So finally it turns out to be negative L, and then cosine of omega t. But we have something else, is that we have the chain rule, okay? For the chain rule, we have this omega, but 2 times, so we have omega squared. So it turns out to be negative. We should still have this Q, okay? This Q is still there. So from here, okay? So it turns out to be L omega squared Q cosine omega t. Okay, and then we have a negative L, and then omega squared is 1 over LC, okay? And then times Q cosine omega t. So we can actually cancel this L and this L. So it turns out to be negative Q over C, and then cosine omega t, and then which is nothing but negative V cosine omega t. So it turns out to be negative 57 cosine of t. And then omega, we can just plug in the value of L and C. Okay, so which is omega is 1 over square root of LC. So it is 0.12 times 10 to negative 3rd power. And then times the C is 1.5 times 10 to negative 6. Something like this. Okay, so finally, this answer will be negative 57 cosine 7,500 T, of course in radian, okay, if we need to make use of calculus, okay, here we use the derivative here, so yeah, for 99.999%, okay, of the time we need to use the radian, okay, rather than the, yeah, so the radian. So this is in radian per second. Okay, so this is the answer to question A, and for answer for question B, okay, so for the question B is what is the maximum rate, okay, di dt max, okay, at which the current I change in the current, okay. So of course we need to find I first, okay, and okay, so we have I will be dq dt, okay, dq dt, and then q, okay, so just recall it is q equals capital Q cosine omega t, okay, so dq dt will be capital Q, and then cosine turns to be negative sine omega t, and then we have omega as, for the chain rule. Okay, so this is negative omega q cosine, sine of omega t, and then we need to find di dt, and then we would like to set it to maximum. So di dt will be, taking the derivative of it, will be negative omega square q, and then cosine of omega t. Okay, so this is pretty straightforward. The derivative of sine turns out to be cosine, and then we have the chain rule, so we have an additional omega multiplied to the whole thing. So, so to make it maximum, di dt max means we try to make this, okay, cosine of omega t to be -1, okay, combining with this one, okay, so it turns out to be omega square q, okay, so here cosine omega t is equal to -1 at this for this condition. Okay, so here we have omega square will be 1 over LC, and then q, so q over c will be v over L, so it turns out to be 57 over 0.12 times 10 to negative third power, which is 4,800. Okay, so here we need to determine the SI units. What is the SI unit? So you need to pay attention to this one, di dt, okay, which means that the SI unit will be the SI unit of the I, which is A, okay, ampere, per dt. T is time, okay, so the SI unit will be S, okay, so the whole SI unit for the di dt will be A over S, okay, A over S, ampere per second. So this is the question for the second question. Yeah. Okay, so maybe let's have